Okay, so in this lecture, we have our last section of Chapter 17 here, and we'll be talking about moving reference frames in a more general sense than we have been. So the last section was about, last couple sections where we had velocity and acceleration of two different points. We were talking about in terms of these like sliding contacts where we have, we want to know in an absolute motion in terms of the absolute velocities and accelerations, that's with respect to a primary reference frame, how do A and B relate when one of them's on, they're basically on two different bodies rotating independently of one another. And so in these slider contexts, like writing these relative motions in terms of the relative velocity that you see here and this relative acceleration, were a bit manageable. Like we could actually do that, right? And that's because there's only like one direction in which the thing could be sliding relative from one to the other, right? But this can be extended, this like notion of having a body fixed reference frame and a primary reference frame and relating the two to any reference frame. Okay, and so this is all kind of review so far, and now we're just going to do is to basically say, hey, we can extend this and talk about how we go about extending it and what happens when we do extend it, and if we can, cancel out terms like we've been doing even with the slider ones. So all of these relationships are applicable to any reference frame that is moving with origin B, right? So like in our example, B is the one that, B would be the reference frame in which we take A relative to, A motions relative to. So that's going to be applicable here, right? B will have whatever origin, of the reference frame we choose. Well, let's choose it to be B, is basically what we're saying here. Angular velocity, omega, right? So that would be the angular velocity of the reference frame. Angular acceleration, alpha, right? Because that shows up right there. So if that reference frame has angular acceleration alpha, all relative to a primary reference frame. So this whole statement is to put some structure onto something that we're basically just saying, like, this can be used anywhere as long as we know these quantities, right? So that's just a general statement, like extending this to any sort of transformation or conversion between two different reference frames. Now let's talk about specific reference frames that we call inertial. And again, this is probably something that you've heard these words before, and in fact probably used them in terms of the technicalities of them. But now we're at the place where we can say, well, what does it actually mean to be an inertial reference frame? You might say there's, it's not accelerating, right? Well, that's not exactly true. All that's true is that this is going to be, a reference frame is considered inertial when Newton's second law applies directly. So we can apply Newton's second law, and let's add with no modification. Or as long, I don't know if with no modification, I mean, we're going to talk about some modifications to make, but like an inertial reference frame means that you can apply Newton's second law and it's a valid physical law. Okay, so remember Newton's second law is the name of the game in this whole class, and it says that external forces applied to an object causes acceleration or are directly related to its acceleration where the mass is up front. In fact, more general, right, it's a rate of change of momentum over here. Okay, so let's take an example of this and of a reference frame, and then let's ask if it is inertial, and if it's not, why is it not, or what do we have to consider? What kind of physics do we have to consider in order for it to be inertial, right? And so we should all be familiar, because we experience this every single day of our lives, Earth. Okay, so the planet we live on. Let's take that as the reference frame. Okay, so the Earth rotates about an axis through the north and south poles. And I'll draw a picture here in a second. Let's just do it now. Okay, Earth is obviously spherical, approximately in nature, so I'll represent that with a circle in 2 dimensions. But right down through the middle And it's actually a little bit off axis, so if we want to make it, or it's a little bit tilted would be the axis, but you know, whatever. We'll do the best we can there. North-south. And it rotates, right? About that axis. Okay, so we got an omega rotation. Now, we often use, like in a lot of our analysis, like the reason for talking about this is like, first of all, get a feel for like how we have to be careful with applying these relationships when we go to extend it, but also to talk about why we apply Newton's second law when we are on a reference frame that might not be inertial intrinsically. Okay, so we often, in like, you know, in a lot of the problems that we solve, we just use a local Earth fixed reference frame without really thinking about it too much. We just say, well, this is obviously going to be the right analysis to do, and we can obviously apply Newton's second law here in terms of the forces we are analyzing. And then we impose it to be inertial. Okay, right? So we just assume it's inertial by saying, well, it's only the forces of friction and gravity and the normal force. And those are the only ones there, right? Okay, so that means that what we apply is sum of the forces equals mass times acceleration. Yeah, and I'm gonna add to this in a second, right? First, let me say what it means to be a local Earth fixed reference frame. Like, what are we actually picking here? Okay, so let's say okay, so we got the origin. Or let's say we've got like a good choice for an origin, which would be kind of like the center of the Earth, right? And so at that place we would have a reference frame or a coordinate system defined. And maybe this one looks a lot like a Cartesian, whatever it is, right? Just three axes defined. Doesn't matter so much how we're doing it, but just like we affix a reference frame with that coordinate system there. So O is going to be the representative, or at least a origin of an Earth-centered, non-rotating, because it doesn't need to move if we put it right at the center, right? Right at the point where there is no rotation. It's a non-rotating reference frame. Okay, so from that perspective, it is fixed, not moving, as a like with relation to somebody like way out, like our perspective, like somebody just watching the solar system act, right? So something like this far away view. Okay, then we go to like the surface of the Earth somewhere, which is where we live, and let's say we've got point B here. Yeah, let's put B here. And now, when we go to analyze this, maybe we put the north direction. So this is supposed to be on the surface of the Earth. So let me put like a line of longitude there, right? That would be, so there would be another one over there, right? Because it's a sphere, it's kind of coming out at us. So the north direction, if that's what we chose, would be, you know, the y direction, whatever, would be there. And then we would have in the directly east direction would be one, and then directly north, or like, sorry, not north, upward, out of the surface of the Earth would be the other direction, right? So I don't know, maybe that would be the choice of reference frame. I don't know if you can see that, right? North, east, and then that would be directly tangential, normal to the surface of the Earth there. Okay, so let's say at B, I mean, that's what I mean, like that's where we live. We often like choose these reference frames as our as the reference frame to do analysis in. So this B here is our Earth-fixed reference frame that I referred to in my description of what we often do with Earth when we do our engineering problems. Okay, so if we do analysis here, with that being our fixed coordinate system, and then like out somewhere, you know, it's not necessarily out in space, but we're analyzing an object moving somewhere in space, and this really doesn't matter where it is, right? We got our two reference frames on there. This is now just another object that is maybe moving, and we're talking about like, oh, what is its motion? What is its velocity? Well, we have to say, well, velocity in terms of which reference frame are you talking about, right? Because B is now rotating, right? It rotates with respect to the primary O, right? So think about O is primary, B is secondary, and it's rotating. And we often don't consider that it's rotating, right? Okay, so so in terms of the Newton's second law part, right? If B, well, actually, let's add what A is here. So A, okay, so A, maybe define everything. This is an object whose motion, so whose dynamics, right, is we're looking to characterize. We're looking to analyze the dynamics of that object, right? And we can choose a reference frame in which to do it. We often choose B when we're, that's actually rotating in terms of the fixed coordinate system O there. Okay, so because B is truly rotating, it's not really inertial, right? Basically, we can't just apply this with the forces that we are assuming. There's additional components of acceleration, right? Which is here, right? Yes, this is the this is what we'd like to do, right? Newton's second law would work for this, right? Sum of the forces equals mass times this acceleration. But we often just look at the acceleration relative to the reference frame. And if we do that, then we have all these other terms that we're leaving out. Everything but this term, right? So really when we do our analysis, we have this. We don't really realize that we're doing that. And that's all we do. Right? This is how we apply Newton's second law. But what we're intrinsically assuming, and spoiler alert, most of the times this is okay. We basically throw out the rest of these terms, which is mass times, I'm just gonna list all the rest of the terms except for that one. Mass times acceleration B, and I think we're gonna need a few lines here to fit them all in. Acceleration of our reference frame itself, absolute, plus 2 omega crossed into VA relative, plus angular acceleration. Oh, and by the way, this is maybe go back to our diagram. We'll put a little E there. That's omega of the Earth. So anything subscripted with a capital E here is the motion of the Earth, because that would be the relative. It would be the the relative rotation of B due to compared to O, relative to O, right? So this is the angular acceleration of the Earth. We'll talk about that in a second. That's the freebie. That's the one that's that we can throw out quickest. And then the last term would be angular velocity of the Earth crossed into the angular velocity of the Earth crossed into the relative position of A from B. Okay, so now the analysis that we do end up doing for a lot of our engineering problems assumes basically that all of these terms are negligible. So if these terms are negligible, and we can convince ourselves of that, then our reference frame is inertial. And that's kind of a definition of the inertial reference frame, right? And Newton's second law applies directly. Okay? All right. So let's talk about each of these terms. Each of these terms that we are neglecting for the scale of the Earth and doing an engineering problem at B, looking at object A here, where usually A is right on in the laboratory, right? It's something that is really close to B, or the origin B of this reference frame, right? Okay, so the first term here is the acceleration of the reference frame itself. So right, this is the acceleration of basically the laboratory itself. It's the acceleration of that point on the surface of the Earth. So this is the acceleration of the Earth fixed reference frame. And now this one is actually one of the more tricky ones. Oftentimes this is included in our gravity. So if we're including gravity, if we have a local value of gravity, of the gravitational acceleration. So if we are using, the local value of acceleration, this is actually included, right? The fact that the Earth, that the reference frame is accelerating, that's often wrapped into how we get to the gravitational constant, the gravitational acceleration, I should say. And it's often, if we're not considering it, these changes are typically pretty small. The next term here, 2 omega e. I think, yeah, we're keeping them in the same order that I wrote them on the last page. All right, looks like that. This is what we call the Coriolis acceleration. Now, I've actually done some work with oceanic dynamics, ocean circulation, and this is a huge one because we're talking about the scale of the ocean. Okay, so this is significant, and you do need to consider this term. You can't throw it out if the object's velocity is large relative to the Earth's rotation. Okay, so if the object starts to move in a significant speed compared to, so that as it's moving, the Earth is also like getting out, sweeping around it, right? Or maybe the Earth, the motion relative to the surface of the Earth. So maybe the surface of the Earth is sitting here at my point, and I'm trying to fly overhead or move overhead. If I'm moving much faster than the Earth's rotation, right? Well, let's say moving much slower, then the relative motion here, right? My finger's barely going to go forward. If the rotation of the Earth is there and I'm just slowly creeping forward, then there's nothing to be, But if they're about the same speed, and as the rotation goes, and that's about my speed, there's going to be this problem where my motion kind of looks like an arc, right? And that curving of an arc is a result of the Coriolis acceleration. So if those are about the same magnitude, then we do need to include this. Now, oftentimes, right, if we're just looking at doing some structural analysis, or if we're just looking at flow around a car to see, flow around a car to see if we should, what the aerodynamic drag is on the car as we're designing that object, or some robotics element where everything's kind of localized in terms of like a lab scale, then this isn't going to be that important, and we often just ignore it. Okay, the next term looks like this, and I said this was the free one because I'm just going to make the bold claim this is 0, right? And that's because, and I guess it's not perfectly 0. There's going to be nothing's ever perfectly 0 in the physics world, right? But it's a pretty fair assumption to say that the Earth's rotation is constant. All right, so basically that we're saying that 0 vector, the acceleration of the Earth is 0. Okay, all right, just it's rotating at a constant speed, and that's not exactly true. There is some small. We're actually being dragged down by the Earth-Moon system, right? And that's showing by the tides, right? The fact that we have like a lot of liquid on our surface, we call it water, and that dragging of the tides as the tides get pulled towards the moon, and the moon rotates around us, so we're kind of dragging the water around. That actually takes a little bit of energy out of the system, and our rotation actually is slowing down a little bit, but it's very, very slow change in the rotation rate. So we'll just say that one equals 0. And then this last term looks like that. And this last term, if you just work through the scale of these numbers, this turns out to be very small. And now, very small is a subjective word, so it depends on the scale of the physics you're looking at. But the rotation, this is the rotation, the angular velocity of the Earth, which is, well, we rotate 1 rotation per day, right? And if you convert that to radians per second, that turns out to be 7.27 times 10 to the minus 5 radians per second. And so what it turns out to be is if you're looking at objects, well, let's just give a number here. So for objects at an altitude of 10 kilometers, this term turns out to be, because this is also going to be scaled up by how far away it is, right, from the surface of the Earth, Right? Often we use the surface of the Earth as the B reference frame, like a reference frame to be a fixed Earth fixed, and then we go up, even up to 10 kilometers, which is really high. Like we're going well into the atmosphere here. This term is about 10 to the minus 5 meter per second squared. So if our motions are significantly have a much higher acceleration due to the forces involved, then this term we just neglect. So in the end, after saying all these four things, I'm back to where we were, right? Where we came from, right? We say like, well, we often just do this. We just live at B, we analyze systems at B, we do experiments at B, and then we often ignore the fact that the Earth is actually rotating, and we should be including all these things, right? Earth's rotation shows up there, there, and there, right? Well, we include this in terms of little local gravitational changes, but these are they important? Well, they're only important when we're talking about motions, and in fact, it's really mostly this term. This term becomes important on the scale where motions are on about the same speed as the Earth's rotation is at these outer, the Earth's rotation out at this place on the surface of the Earth. So let's make some conclusionary statements here and kind of wrap this up. So for laboratory scales up to like even citywide. So if you're talking about how even if we get to, well, no, but I think anything more than a citywide. So what I mean is like how wind sweeps through like a city or a region of the country, let's say. Anything on these scales, and the engineering applications for laboratory scale up to citywide scale engineering applications. These terms are negligible, and Newton's second law applies directly in the Earth fixed reference frame. So that's the claim, and that's what we do a lot in our analysis. Okay. Now, if a term does turn out to be significant, so if one of these terms, after our careful analysis and comparing the scales of the system, if one of them turns out to be non-negligible, like what I said, this one, that's the most likely candidate for one that we need to be more careful with, called the Coriolis. Well, it's a Coriolis acceleration. Then we can include it. We can have a modified Newton's second law here. So the way this works, so let's write this out. If a term turns out to be significant, something that we do need to include, the non-negligible term, or terms, so like this one, let's say, right? That term, we can actually enter it into Newton's second law as a force, right? We can go back to here and say, well, we'll just have acceleration over here, but like this term here, now we can treat it like a fictitious force and put it over to this side, right? And just add it in. Just think about like, well, the Earth and the fact that it's rotating. So we'll do analysis in the Earth in the Earth fixed reference frame. I'm sorry, the Earth fixed reference frame out on the surface here. And the fact that that is rotating, we'll say, hey, there's another force there, even though it's not actually part of our system. It's just like the Earth and its rotation are sort of causing this force. It's it's a fictitious thing to represent a rotating reference frame. All right, so this is this is like a place where like the math can actually modeling the system works out perfectly. So if a term is significant, the non-negligible term is included in our Newton's second law as an additional fictitious force. Okay? So let's talk about this Coriolis acceleration. So for example, we often include a well, we call it a Coriolis force when it should always be in quotes. There's not actually another force there, right? And so this force, in quotes, caused storms to rotate in a particular way. So if we are in the northern hemisphere, counterclockwise, and we'll do a picture, we'll do a little drawing here why, and then clockwise in the southern hemisphere. So we get different, so we're talking like big hurricanes here, big storms. They actually rotate in a particular way. So let's see how this works, right? So what happens here is we modify Newton's second law to say, well, sum up the forces that are actually on the object. So like little particles of the clouds and the little particles of the particles in the air, and they then accumulate to make these big storms, let's say, right? The energy up there. And then we add this term on the left-hand side as an additional force. Okay. And then this equals mass times acceleration, A relative. Well, all we do is actually just, this comes naturally. Like, this is how we analyze the system. So some of the forces in that Earth fixed, B reference frame, and then there's the acceleration relative to that reference frame, right? This is that Coriolis force. Okay, quotes. And let's see. Let's see if we can convince ourselves why storms, due to this force, why storms rotate in a certain way. Okay, so let's do this with a fresh new drawing here of the Earth. And now this is we have to actually take 2 steps to get to the point where we are talking about the direction of rotation for storms. So first, let's first start with the Earth. We'll put this north-south axis of rotation, represent the rotation with the rotation of the Earth. Now this vector is actually going to become important. And we'll also put on here the equator. Oh, maybe we'll make it nice and solid, because it differentiates the north and the south, which you said there's a different actual phenomenon going on here. We'll also put lines of longitude. Okay, just to give it a nice spherical look. And we'll do our best to describe this Coriolis effect. Okay, so hopefully that's jumping out a little bit at us here. And we want to do this here. Go to a place on the Earth. So let's say we're down here. Let's actually say we're in Montana. Okay, so that's going to be I don't know, right about here-ish. And let's say we have a particle. Maybe throw something downward. Actually, I like going up. So let's say we're down. We can do the same thing over here afterwards. I like going north, so we can do the same thing in the south. It doesn't really much matter. Let's start here and say we throw a ball, or maybe a big paper airplane to the right. So we're down in Texas trying to throw something. What's actually, no, New Mexico or something. And we're trying to throw it directly north to get to Montana, right? To land in our backyard or whatever. Okay, so this is then our relative velocity in the for the Earth fixed reference frame of Texas or whatever it is, right? We're trying to throw it directly north, but what ends up happening here is because the radius here, so from the axis of rotation, right, that is bigger than where we're trying to shoot to, which is up here. A little bit less, right, coming out to these lines of longitude. So Montana is closer to the axis of rotation of the Earth than New Mexico is, right? So we throw it directly north, but this angular momentum of having angular momentum by being at a bigger radius here is conserved. So as we throw it up, basically this is going to be spinning faster, and therefore it turns to the right. So that's kind of the main idea of the Coriolis effect, is as it goes, we turn to the right. But this also shows up in our force. So let me get the equation back up here. Remember, this is all stems from, we have the sum of the forces, which would be the external forces acting on this particle. But even if we assume those are nothing, we see a motion of this particle. It doesn't just act in a straight line per se. So you're like, oh, Newton's laws don't work. Well, they do work. It's just this is part of the acceleration, because we actually are moving with the rotation of the Earth. So, okay, so like even if we're saying this term is nothing, there's still going to be motion in this like circular pattern, and it ends up being this way, always turning to the right. Now let's analyze this from this term, right? This acts like a force. So let's say we do this for we have a particle moving north in the northern hemisphere. Okay, and so then we have right-hand rule, right, from this term, like what forces it felt. Well, you got omega E, which is straight up the axis. And then you have to actually bend your fingers a little bit down, and that's because moving north is kind of tilted toward inward, right? So we've got to bend this inward, and then so the effect would be to the force would be to the left, or well, I guess I should say omega cross V would be to the left, right? Would be westward. But this is negative, right? So it flips it to the east. And so as the particle goes upward with the velocity, right, relative velocity to the Earth fixed reference frame, it turns to the right. Okay, so particle moving north in the north turns to the right. Okay, and we can actually write out our vector product here. I would write it like this, right? Omega E is basically straight up. The velocity is kind of inward a little bit, right? It kind of goes. It has to like bend kind of toward the center, toward the axis of rotation here, which is not straight up. Right there's omega E. This is bending that way. So this is VA relative to go directly northward on the surface of the Earth, and so then our omega cross V is to the left, but the negative version of that would be to the right. So that would be like something like that. This is minus omega E crossed into VA relative, right? And so the force, the fictitious force felt by the particle is always to the right and going in this circular pattern. And so if we had this motion, if we're up here in Montana throwing it southward, always bending to the right, and it creates this pattern. Now you might notice this is all clockwise, and I said before that there's a counterclockwise rotation in the northern hemisphere, and that might be troubling to you. Well, that's what I mean. This is a two-step process to actually talk about storms. But let's first talk about what happens in the south, and then we'll say what actually happens in storms. So let's do the same thing where we have a northern moving particle in the southern hemisphere. Okay, so particle moving north, now down here, and so let's make sure we differentiate these two phenomenon, because there actually is a difference. So this is my northern hemisphere analysis. Down here I'll do my southern hemisphere. So we'll do the exact same thing. We have omega E now is straight up and down from the right hand rule, but now our velocity is omega, and we actually have to like come a little bit outward, right? We have to like, that now points away from the axis of rotation, so it'd be right hand rule, point outward from the surface of the Earth. Omega cross V would be to the right, but flip it to be negative to go to the left. So I don't know how to represent this on this plot here. It's kind of like, well, if you look at that, that would be the kind of outward. It should be out, kind of bending out of the page. VA relative. And so then omega cross V there would be kind of that way. At that point it would be like that way, but it's negative, so it ends up being pushing it to the left. Minus omega E crossed into VA relative. So the force, in quotes, right, the fictitious force felt by this particle is pushing it to the left. So turns to the left. Turns to the right in the northern hemisphere, right? So northern hemisphere particles are constantly turning to the right. Southern hemisphere. And it really, at its heart is related to this, how we started this, which is to say, here this particle is moving to higher angular velocities, and this particle is moving to lower angular velocities, which makes it a change in the behavior. So this particle is going to take on that path. right? I mean, it's not ever going to come off the surface of the Earth, right? But it would kind of wrap that into on the surface of the Earth, and it would make that pattern. Now, this now looks counterclockwise, that looks clockwise. So when we talk about storms, for storms, this is still true, right? Particles turn to the left, particles turn to the right. It's just the motion is a little bit more complicated, or convoluted, let's say. So for storms, we have air particles constantly moving, air particles constantly move, not plural, toward the low pressure center. So a storm is governed or really characterized by these like really low pressure centers. And so like this is like the eye of the storm here, and air would then be trying to constantly be moving toward the center. That's what like a low pressure does. Okay, but right, so if we're in the north, I'm just going to do this just for the north. So I'll take this here. In the northern hemisphere, okay, this southward movement of the particles that are north of the low pressure are constantly turning to the right. So it's actually, I'm going to do the one on the bottom here first. So this one constantly turns to the right. This one constantly turns to the right, constantly turns to the right, to the right, to the right, to the right, right? And in the end, you get this global movement of the storm moving like that, which is actually a counterclockwise rotation, which is why you see hurricanes that kind of have this overall sweeping effect. And I actually lived on the coast for one of the big ones, and I remember what we got was we got hit by one of these like long tails that kind of get shed off the end here. And what happens with these ones is it's like a big surge of water comes in as this you get all of this sweeping effect in the low pressure center in the middle. But right, they're nothing to be taken lightly, right? There's a lot of energy in these storms. Okay, so this is a bit of, I'm kind of ad-libbing this one a little bit here, a little bit disorganized, but it's it's not a key component, but I think it's of interest to really talk about why we analyzed in these Earth fixed reference frames when we actually have a rotating reference frame. But we often neglect it. But when you get to the scale of like continent-wide or ocean scale, we do need to include these. They're really accelerations that we're ignoring in other situations. But it's kind of cool because we can just include them as a force, right? We can put them on the force side of the equation, and then we can let that determine what the local acceleration is. And then even without any external forces, we just have particles that are moving on the surface of the Earth. They look like they're being forced, right? They're constantly being turned in this pattern here. Okay, so other things, let's just end this off, like where and what, where Coriolis, in what systems force is included. Okay, so we've already talked about like these Earth systems, but some other examples, if we're not drawn, right? When we talk about like rockets that travel up to space, when you have long range ballistics, right? Those travel across continents, across oceans. These things, to get the trajectory exactly right, need to consider the Coriolis force. Any weather analysis needs to consider this, like where storms are traveling, where big, low pressure systems, high pressure systems, ocean currents, any statements we ever make about climate, all of these things need to include. So that's both the atmosphere and the ocean need to include the Coriolis force. Okay, so so that wraps up chapter 17. Okay, so a bit of review here now. The first section here we talked about was kinematics of particles, right? So describing the motion only and not talking about the forces involved. We first started with rectilinear motion, which is 1D, where motion didn't need a vector description, right? It was all done by scalars with position s, velocity v, so really just the speed and some direction, either left or right, and then acceleration. We talked about 4 different types of problems, right? 4 different ways acceleration could be specified, right? We can know acceleration as a function of time, a constant acceleration, acceleration specified in terms of velocity or in terms of position, and that changed our analysis. We then talked about curvilinear motion, introduced ourselves to the difference between Cartesian, natural in terms of normal and tangential components of the motion, and then the polar description of motion, right? And worked through problems that way. And then we talked about relative motion, right? So what it means to have two particles moving, and how we could, from our coordinate, from our choice of coordinate system, we could express the motion, whether it's position or velocity or acceleration. We could either go, just talk about the absolute motion of A, or we could express A's motion in terms of B's motion plus the relative motion of A with respect to B, or from B's perspective, right? Okay, then, right, that's just kinematics of particles. Then we moved in kinetics of particles, right? And we talked, now this is actually talking about what forces, how the forces cause that motion, right? Cause the kinematics that we first started with, right? And so the kinetics, right, came in 3 flavors, right? We could just directly apply force, mass, acceleration relationships from Newton's second law. We could then dot this with along the path direction and integrate it, and then we get work and energy, right? And the result there was energy at the start in terms of its kinetic and potential energies equals the energy at the end between 2 different states. We have 2-state analysis here, where if there is any non-conservative work like friction, anything else that's path dependent, we do need to integrate that energy loss across, along the path direction. Where this becomes a good technique is when we can cancel that out, or like friction, right? We know maybe a constant friction case, then we kind of know how this behaves really well, and we can determine this term. But if anything gets really complicated, like when we get to impacts, this is not going to be a useful tool. Right, so that led us into linear and angular momentum analysis, and really the conservation of linear momentum was our main focus here. And what that was, right, again, more 2-state analysis, where here we use this just to go from right before a violent collision to right after a violent collision. I use the word violent, I don't know if it's appropriate, right? It's just saying, like, I'm trying to express how this would be a complicated analysis during a complicated collision, a complicated impact scenario, where the losses, the non-conservative forces at play could be significant, right? So oftentimes we'll take a system where there is the impact of 2 particles or 2 macro scale objects that can be treated as particles, and we'll be doing energy analysis, but and then we'll do energy analysis right before we get to that collision. During the collision, we apply momentum, and then we go back to energy analysis afterwards, right? And then lately, we've been spending quite a bit of time to just basically get to these 2 relationships. So everything above here was for particles. Now we have analysis of rigid bodies. Remember, rigid bodies are defined where A and B are at a constant distance from one another, right? They're on the same body, therefore they're rotating together, and they basically, that would be a scenario where the relative velocity between the 2 points is 0. And so we first started deriving that equal, so I'm going to try to cancel those 2 relationships. This is rigid body kinematics, by the way, right? We then extended it to say, well, what if it's not rigid body and we just have like a sliding contact, or just more generally we're going from one reference frame to another reference frame, and then we get this more general relationship. Okay, so in that context, the rigid body is like, well, the rigid body itself could be rotating, could be having an angular acceleration that's non-zero, and a more general description. And actually ended off, with a talk about how the Earth is a rotating reference frame, and how we oftentimes cancel out these terms, but they're always there, but we're just kind of neglecting that they're there. Okay, so I think that's a nice review of the content so far, right? This is kind of a lot. Like I said, we're over halfway through the material,